Today we're going to do some more with probability distribution. So we're going to continue on with finding mean, but we're also going to look at how to find standard deviation and then determine what's typical and what's unusual for a probability distribution. So we're going to take a look at the spinner on the right. And as you can see, the different outcomes are 1 through 5, but the odds of getting 1 are a lot higher than getting a 2 or a 5 because the chunk for 1 is bigger than the chunk for 2 or 5. So we have a table showing us the different outcomes, 1 through 5, and the probabilities of landing on each individual space. So what we're going to do is we're going to start by finding the mean, or mu, because in order to find standard deviation, we have to know what mu is first. Okay, so this first additional column is going to be x times p of x. All right, so we're going to go through and we're going to figure out what the x times p of x values are. So if I do 1 times 0.34, I get 0.34. If I do 2 times 0.11, I get 0.22. 3 times 0.21 is 0.63. 4 times 0.18 is 0.72. That's a 7. And then 5 times 0.16 is 0.80. Okay. Now if I go through and add all of those numbers together, I get 2.71. So that means the mean of this probability distribution is 2.71. So what does that mean? That means if I were to spin this spinner a bunch of times, on average I would end up getting a roll of 2.71, which obviously there's no 2.71 anywhere on the grid, but that's what it would come out to. So it would be between 2 and 3. All right, so now how do I use this to figure out what the standard deviation is going to be? So we start off by adding on another column, and that column is x squared. Okay? And that's because in the standard deviation formula, we have this. So standard deviation, sigma, is equal to the square root of the sum of the x squareds times p of x. Okay, so we do that sum, and then we subtract the mean squared. We do the square root of the whole thing. Sorry, it didn't quite fit on one line there. Okay, so we need x squared, and we're going to eventually need x squared times p of x. Okay, so x squared is again going back to the original numbers over here. So I'm squaring these numbers. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. And now I'm going to take this column, x squared, and multiply it by the p of x column right here. So now I'm doing 1 times 0.34 is again 0.34. Now I'm going to do 4 times 0.11 and get 0.22. And now I'm going to do 9 times 0.21 and get 1.89. And I'm going to do 16 times 0.18, and I'm going to get 2.88. And I'm going to do 25 times 0.16 and get 4.00. I'm going to add all of those numbers together, and that comes out to be 9.55. Okay? So, where do we go from here? Now what we're going to do is we're going to plug the numbers into this sigma formula. So back over to where the green is, I'm going to have sigma is equal to the square root of that number we just came up with, 9.55, minus our mean, 2.71 squared. Okay? So that, when I type it into a calculator, and you can type that all in at once under the square root, you come up with 1.49. So the standard deviation is 1.49. So we have a mean of 2.71 and a standard deviation of 1.49. That's how you find standard deviation by hand. You can check this using a graphing calculator by typing in the numbers for x into L1, the numbers for p of x into L2. So now we're going to take a look back at the example we looked at yesterday with the rolling of 2 dice to figure out how to find standard deviation without the calculator. And again, the standard deviation formula is written right at the top here. So we had gone through and we had filled in what all of the p of x values were for this. So the first one was 1 out of 36. then it was 2 out of 36, 3, then 4, then 5, and then 6, and then it went back down. 5, 4, 3, whoops, 2, and 1. Okay, so those are all the probabilities that we got in class yesterday. So now we need the x times p of x. And we had done that yesterday as well. Okay, so I'm going to shorthand it. These are all out of 36, but I'm just going to write down all the numerators to make this a little bit quicker. So I've got 2 out of 36, then 6 out of 36, 12 out of 36, 20 out of 36, 30 out of 36, 42 out of 36, 40, 36, 30, 22, and 12. And again, these are all out of 36. Okay. All right, so to find standard deviation, we need x squared times p of x. So we're going to write down what the x squareds are. And again, x squared is coming from the x values being squared. So 2 squared is 4, 3 squared is 9. So I'm basically just going through and listing all the perfect squares starting with 4. 25, 36, 49, 64, 81, 100, 121, and 144. Okay, and then this last column, we're going through and we're identifying what x squared times p of x is. Okay, so x squared times p of x. So I'm doing these numbers that I just wrote in orange times the initial p of x values. Okay, so those numbers are going to come out to 1 times 4 is 4 over 36, 2 times 9 is 18, 3 times 16 is 48, 4 times 25 is 100, 5 times 36 is 180, 6 times 49 is 294, 5 times 64 is 320, 4 times 81 is 324. 3 times 100 is 300. 2 times 121 is 242. And 1 times 144 is 144. And I apologize if this isn't really the easiest thing to read, but that's why I was saying all the numbers out loud as I was writing them. So what do we need? We need the sum of the numbers in the final column here, and we need the sum of the numbers in the x times p of x. Okay, so the x times p of x is our mu, and we had found that before. That was 252 over 36. So the mean mu is 252 over 36, which comes out to exactly 7. And then the sum of the x squareds times the p of x values, that comes out to be 1,974 over 36. Okay, so now we're going to plug them into that formula up top. So the standard deviation, sigma, is equal to the square root of 1,974 over 36 minus 7 squared. Okay? And I just want to warn you that if you're typing this into a calculator, you're doing square root, and then you see a set of parentheses, and then you open a new set of parentheses and do 1974 divided by 36, close one set, minus 7 squared, or minus 49, and then close. Okay? And this comes out to be approximately 2.4, which is the same as what we had found when we did it on the calculator yesterday. Okay, so what's the purpose of having these numbers, and how do we figure out what's typical, unusual, and so on? So, using probability to determine what's unusual. So, X successes among N trials is unusually high to have that many successes if the probability of X or more is less than 0.05, or if it's less than a 5% chance of happening. Okay? And we'll put this in context in a second. All right? X successes among N trials is unusually low if P of X, or less is less than 0.05 or 5%. So you can kind of think of it as a 5% rule. All right, so we're going to take a look at our examples. So I have one little change that I want to make to this. So it says, is it unusual to have only 3 baby girls out of 14? We're going to change the only to say no more than. Okay, so is it unusual to have only 3 baby girls or no more than 3 baby girls? So that means you have X is 0, X is 1, X is 2, or X is 3. Okay, so what we want to do is we want to go through and we want to find the probability of 3 or less. So that's the probability of none plus the probability of 1 plus the probability of 2 plus the probability of 3. And remember, this was out of 14, and these are those decimal values that we had come up with yesterday. So if I go through and record what those probabilities were, the first one was essentially 0 because it was less than 0.001. The second one was 0.001. The third one, P of 2, was 0.006. And the fourth one was 0.022. If you add all of those together, you get 0.029, which is only 2.9%. So there's only 2.9% chance that out of these 14 babies that they randomly selected from a hospital nursery, that 3 or fewer of them would be girls. So it would be unusually low to have 3 girls in that group. Okay? All right. If we go back to our other example, rolling 2 dice, is rolling a 10 an unusually high value for rolling a die? Okay? So if we take a look at that, so this is like saying, what's the probability of getting 10 or more on a single roll? Remember, this is on a single roll. What's the probability of getting a 10 or an 11 or a 12? So we're looking at the probability of getting a 10 plus the probability of getting an 11 plus the probability of getting a 12. So the probability of rolling a 10, that was 3 out of 36. Probability of rolling an 11, that was 2 out of 36. On the probability of rolling a 12, there was only one way to do that out of the 36 outcomes. If we add all of those together, we get 6 out of 36, which is 1 out of 6. And if I do 1 out of 6 as a decimal, that is 0.16 repeating, okay, which is approximately 16.7%. So the answer is no. It is not an unusually high roll to get if you get a 10, because this exceeds that 5% rule that we had in the previous slide. Okay? So in the first example, yes, it was unusually low to have no more than 3 baby girls. Here, no, it is not unusually high to get a 10. Something that you could kind of expect to get. All right, the last thing. And this is probably the easier way to determine what's typical and unusual. This is a little bit easier to understand and also a little bit more familiar than that 5% rule that we were just talking about. So determining typical versus unusual values in a probability distribution. So to get a typical min and a typical max, we use the same general idea as what we did when we were doing typical min and max using mean and standard deviation before. So to do the typical minimum, we do our mean minus 2 standard deviations. And then to do our typical max, we do the mean plus 2 standard deviations. So this is just like when we were doing x bar plus or minus 2s. It's the same exact idea. Okay? So again, tying the previous unit in with this current unit. So if we go back and look at the 2 dice thing one last time, 2 dice, and we look at the problem we just did, we were looking at getting a 10. So the minimum there would be equal to the mean 7 minus 2 times 2.4. Oops. And that comes out to 2.2. So getting a roll that's below 2.2 would be unusual. So getting a roll of 2 would be unusual, but getting a roll of 3 would not. The maximum would be 7 plus 2 times the standard deviation, and that number comes out to 11.8. So getting a 12 would be an unusually high roll to get, but getting an 11 would be typical. Okay? So getting a 2 would be unusual, getting a 12 would be unusual, but getting anything from 3 to 11 would be a kind of expected thing to get when you're rolling a die. Okay? So I hope that this was clear. Your homework tonight is to finish your probability distribution worksheet, and you're doing sections 4 and section 5. So you should have the entire packet by the next time I see you.